Hello everyone, my name is Ayman. In this video I'm going to introduce the AD2 Set 4 experiment. In this experiment we will use the nodal analysis technique to find the voltages of nodes of the circuit. For this experiment we need the 1K resistors. You will find a red line for the 1K resistors, and for the 10K resistors you will find an orange line, and for the 100K resistors you will find a yellow line. I will go through the solved example in the manual, and you should follow similar steps when doing the exercise experiment. So our circuit looks like this. Here I'm connecting the first resistor, which is R1, and here you'll find R4, here is R2, and here is R3, and here is R5. And I'm connecting the supply, as you can see, using this red wire. This is the supply voltage. We will use it to connect it to the AD2 board. And we're going to measure the voltages of V1 and V2. You'll find V1 here, which is the common point between R1 and R4. This is V1, the blue wire. And also we're going to measure V2, which is the point between R4 and R5, this point. So I'm going to use the white wire to measure V2, and I'm going to use the blue wire to measure V1. And as you know, we should use two wires to measure each of the voltages referred to the ground. So I'm using another white wire and another blue wire, and both of them are connected to the common ground. So all these points have the same voltage, which is the ground voltage. For part 1, you will see that it shows the analytical solution of the problem. So you can go through these steps and understand how it's solved analytically. And the numbers obtained are V1 here. The theoretical value is equal to 0.415 volts. And V2 here is equal to 0.215 volts. And you have I1 flowing through this resistor. The left one is equal to 0.415 milliamperes, and the current flowing through this resistor, the other one, is equal to 0.0415 milliamperes, and the current flowing through this resistor, I3, is equal to 0.00215 milliamperes, and it will be the same current flowing through this resistor as well because they are connected in series. And finally, the total current flowing through this resistor is equal to 0.4585 milliamperes. So this is the solution for part 1. It's an analytical solution and you can go through the steps. Now for part 2, we're going to verify these numbers using the AD2. So I have connected the circuit as we mentioned. So as we said, we're using this red wire to connect the supply voltage. For this part, we're going to use DC voltage supply, so we are going to use the red wire from the AD2. So the red wire here, which is V plus, will give you the DC supply voltage. I will connect it to this one. And you can use any ground wire to connect the ground. Okay, so this is the ground. And I'm going to use channel number 1 to measure V1, which is the two orange wires. So I'm going to connect one of them to one of the blue wires here. And the other one to the other blue wire. And I'm going to use channel 2 to measure V2. So one wire here to V2, and the other blue wire to the common ground. Okay, so now we have finished our connections to the AD2. Now if we go to the waveform, for this part we are going to use the voltmeter tool and the supplies tool. Okay, so we open the supplies and we open the voltmeter. So for our circuit, we need a 5 volt supply. For this part, we don't need V minus, so we can just leave it off. And we just need V plus, which is the red wire. So we set it to 5 volts. And make sure that the master enable is on. Now we have 5 volts applied to our circuit, and we're going to measure V1 and V2. From the voltmeter tool, click run. And now we have the values, okay? So we have for V1, it's, let's say 0.416. And for V2, it's 0.192. For you, it can be a little different based on the tolerance of the resistance. So it's okay if you have different values, but the change should be very small. And we're going to use these two values for V1 and V2 to measure the rest of the variables, which are the currents. You will find that the total current, which is flowing here, is equal to the 5 volts minus V1 over the resistance value. So it will be 5 minus V1 over 10K, which is equal to 0.4584 milliamperes. To measure the current here flowing through this resistance, it will be V1 minus 0, which is the ground voltage. So we are focusing on the drop over the resistance. So it's V1 minus 0 over the value of the resistance, which is equal to 0.416 milliamperes. For the other one, it's the same voltage, V1, over the value of the other resistor, which is 10K, so it will be 0.0416 milliamperes. And finally, the current flowing here, I3, you can find it by dividing the voltage across this resistance, R5, over the value of R5. So the voltage is equal to V2. So this is the drop over R5, divided by the value of the resistance R5, which is equal to 100K. So you get 0.00191 milliamperes. So this is it for part 2. And if you compare the theoretical values with the measured values, you'll find that they are very close to each other. So this means that your circuit is connected in the correct way. Now for part 3, we are going to measure the power dissipation on the resistors. So the power is equal to the voltage drop over the resistance times the current flowing the same resistance. So for example, R1 here, the power over R1 is equal to the drop over R1 times the current flowing through R1. So the drop is equal to 5 minus V1, okay? The drop over R1 is equal to 5 minus V1, and the current flowing through R1 will be equal to the total current, I told, okay? So if you calculate this relation, it will be 5 minus 0.416, it will be 4.584, times the current flowing through this resistance, which is the total current, which is equal to 0.4584, you'll get 2.1 milliwatts. The power over R2, we apply the same relation for all the resistance. It will be equal to V1 times the current flowing the same resistance. So V1 is equal to 0.416 times I1, which is equal to 0.416. It will give you 0.173 milliwatts. R3 here, it will be also V1. The drop over the other resistance is the same. It will be 0.416 times I2, which is equal to 0.0416 milliamperes. If you multiply them, you get 17.3 microwatts. For R4, the drop is equal to V1 minus V2, okay? V1 minus V2 times the current flowing through this resistance, which is equal to I3. So it will be equal to 0.416 minus 0.191, the difference in voltage, times the current I3 is equal to 0.00191, which is equal to 0.443 microwatts. And finally, for the final resistance, the voltage over the resistance is equal to V2. And the current flowing here is also I3 at this current. So if you multiply V2 times I3, you get 0.365 microwatts. The numbers you get can be a little bit different, as we said, due to the tolerance in the resistance, but it should be very close to these values. And it's very important that you go through the solved experiment steps, as I did, so that you can make sure that you are able to connect the circuit in the correct way and also do the measurements in the right way. For the last part number 4, we are going to apply a sine wave instead of a fixed supply voltage, and it's required to measure the phase difference between the sine waves generated at V1 and V2. So for this part, we're going to use the wave generator tool, and we're going to use the scopes. We need only to make one change to the circuit connection. So I was using the red wire to generate a fixed supply voltage. I will just disconnect this one, and I will use the yellow wire instead. This is the only connection that you're going to change. And now I'm going to generate the sine wave from the yellow wire.
Now we're going to use the WaveGen tool and the scope tool for part number 4. And it's required to use a sine wave. So we use a sine wave with an amplitude of 5 volts. And the offset is 0 volts. And let's set the frequency to 25 kilohertz. And now we run the waveform. And if we run the scope now, you will see that our two sine waves at V1 and V2 should be displayed now, but they are not shown clearly because they are compressed. So we need to scale this range to see clearly the details of the two waveforms. So we stop the waveform, and here if you decrease the voltage per division setting of the two waveforms, this means that you will expand the signal. So that's what we want to do. So we set this one to 100 and the other one as well, so that you can compare the amplitudes easily. And we still are not able to see the details over the time. So we will do the same, but for the time scale. If you observe the period, it's 40 microseconds. So let's say we want to observe several cycles. So this means that our division should be around the same value. So let's say the division should be 40. As you can see, now we can clearly see the details of the two waveforms. Now if you run it again, you'll find that the noise is removed. And now we are able to see the two waveforms, V1 and V2. And in this part, it's required to measure the phase difference between the two waveforms. And as you can see, there is no phase difference between them because our circuit is purely resistive. There is no delay elements in our circuit. So all the voltage nodes in the circuit will have the same phase. There's no phase difference. So the answer for this question is 0. So I hope you found this introduction to AD2 Set 4 useful, and good luck with your experiment.